Good morning, everyone, and welcome back again in our channel. Today we have another application as a mechanical vibration example. We have a spring and mass, and we will find out our differential equation, second order, for this application. So here our spring is unstretched, here is equilibrium, and here stretched from equilibrium. And down is our positive displacement, and we have summation of force equal mass times acceleration. This is Newton's second law of motion. And the forces acting on the system, the first one, a restoring force given by Hooke's law, which is F spring equal minus K Y, where K bigger than 0 and K is constant of proportionality. And K here depends on the diameter of the wire of the spring, the diameter of the coil, and number of coils, and the material itself, the material the spring is made of. And the second one is the force due to air resistance, which is damping force. Try to decelerate the motion up and down. And the force of the air equal minus A times the velocity, dy over dt, where A bigger than 0, it's proportional to the velocity. So here is the M times A equal minus ky minus A dy over dt. And then we divide by m, we got this differential equation. A very important thing and very good question, where is mg? Where is mg? It is not mentioned in our differential equation. So from the equilibrium we have this, and which is in the equilibrium there is no motion. Here mg, and the here k s, the spring force. So here we have this, and when we stretch it, we have summation, the same thing, summation of force equal ma. So we have m d to equal minus k. Here's the distance, s plus y. Then the other force minus plus w mg. Okay, it is plus because we took the downward is positive. So then equal minus ks plus ky plus mg. And from this, we have summation of f equals 0 in the y direction. And so mg minus ks equals 0. So mg equal ks. So this is why we cancel this one. This is why we didn't mention it here in our differential equation. So the solution for this second order differential equation, the quadratic formula for the differential equation is lambda 1 and 2. Here is the formula. And again, we have three choices. If a over 2m, this one, is bigger than k over m, square of course, bigger than k over m, two real and distinct roots. And the solution is this formula. This is constants of, we find them from initial conditions, and we call it as over-damped. Second one, if a over 2m square equal k over m, two equal roots. And the solution here, there is another t here, critically damped. 3, if a over 2m squared less than k over m, we will have two complex conjugate roots, and the solution is here. This is e to the power t. This is the real part of the complex number, and here we put omega instead of a over 2m squared minus km. By the way, if it is pure imaginary, there is no real, so this term will go to 1, because we put, there's nothing here, 0, and we will just have a cosine wave, up and down. Up and down without stopping. Keep going. And here is, if you in terms of the phase shift, we put alpha as a phase shift. The second part is the horizontal system. This is unstretched, this is equilibrium, and here stretch from equilibrium. And here also the mg, where is mg? And in equilibrium, we have this is the surface. This is mg, and this is the normal force. So the normal force cancel the mg. The normal force is of the surface. You can put it here. Normal force. The same also the second law of Newton's second law of motion, and we have a restoring force given by Hooke's law. You have the force of the spring, k bigger than 0, and k depends on the material, the diameter of the wire of the coil, the diameter of the turn, and the number of turns. We have another force, the friction force between the mass and the surface, equal minus c dx times the velocity, dx over dt, proportional to the velocity, this force. And here is our differential equation rearranged, and we got the quadratic formula for the differential equation is the same thing. Three choices. If inside the root bigger than 0, we will have two roots, and this is the solution, two real roots. And if they are equal, two equal roots, and this is the solution, this is the formula. If k over m bigger than c squared over m for m squared, then we will have complex conjugate. We have a special case if the real part of the complex number is 0, then we don't have this term, we just have cosine wave which keep going left and right. Thank you for watching my video, and in this video we finished the homogeneous differential equation, second order. In the next video we will solve the non-homogeneous differential equation, the second order, and see you in the next video.